Okay, we'll get MIT way start in 1 minute. Okay, so let's get started. For people who are remotely, let me introduce myself. My name is Saman Amarasinghe. I'm Ajay's thesis advisor. So how this is going to work is we are going to have an open session. So Ajay is going to first give his talk, and then we'll open up for questions for the open session for everybody in here and also remotely. And then we are going to go into a closed session afterwards with the thesis committee. So one thing thesis advisor get to do in defense is say something about the student. So I was trying to think what to say about Ajay. So one thing I would say is being advisor is a little bit like being a conducting orchestra. You don't do any work, you did others. There's a difference between whether you're conducting a middle school orchestra or Boston Pops. So
Have you ever conducted an orchestra?
yeah. But we
Told it's work.
it's work. Exactly. But with Ajay, it was really fun because we will have some of these really discussions, very abstract, crazy idea. And the next thing I know, it's getting implemented. There are so many cool things happening. So it's a lot of fun to have people like Ajay in your group. So you can have these crazy, weird things and it actually happens. So that's the first thing I want to say. The second thing, I will say three things. Second thing I want to say is uh, most of the time, once you graduate, you spend your lifetime trying to correct bad habits you learned as a PhD student. One bad habit I learned as a PhD student is to never write a paper on time. You're always late, last minute, don't write a paper, and it's not a good habit. And I have been trying very hard to tell my students, no, you have to write early papers. And everybody started listening, and then Ajay came. Ajay had walked into my office normally about 2 weeks to 1 week before paper deadline and say, why don't we write a paper to PLL? Ajay, we have nothing to write about. "No, I think I can do this thing. And we had about two or three even best paper accepted. Didn't get started. The research didn't get started until 2 weeks before the deadline. Now it's very hard for me to tell people, okay, look, we need
Is
to
that true?
start.
Is that true for a thesis too?
Yes. I think that thesis is right now, the draft is about 3 days old.
Yeah.
Okay. That is shown. But Ajay, but he has 3 months to finish it up. So the third thing is very few people leave a lasting legacy in there. This is a very twisted thing in here. Ajay, on the other hand, is a not only good research, he's actually a student leader. He was in all these committees. Every time I look at his name was in some like a student body leadership in there. And one thing Ajay did, Ajay and about 10 people managed to convince MIT graduate student body to unionize. This was crazy because nobody thought that a school with science and engineering people, no radical humanities, can ever unionize and they led the way and then they started this way. So now every time MIT send me this thing, I say you have to fill all these forms. Because the union dictates that. I always will remember you got that legacy last one.
Thanks for the introduction, Saman. Hi everyone, my name is Ajay Brahmakshatriya. I am a seventh year PhD student in Saman's group, and so today I'll be talking about my research, which is just the broad sort of category of this research or the classification is the efforts in democratizing high performance DSL development using the system that we have developed called BuildIt. For this presentation, I usually like my presentations to be very interactive, but since we have some sort of time constraints, we'll still do questions, but like maybe like quick questions, clarifying questions in the middle, and then we can do like long questions at the end. Same goes for folks in the chat. I keep looking at the chat from time to time, but if I miss something, we can do that at the end. Okay, so to get started, I'll start with something hopefully, sorry. I'll start with something that's hopefully very non-controversial, which is writing high-performance software is extremely hard. Now, there are multiple reasons why this is hard for different people, but I'll sort of present my motivation for this uh, through sort of this example that one of my lab mates, Manya, was working on the research ran into in sort of through a coincidence. So before I get to that, a little context, a lot of modern high performance software is driven by libraries. So there are many sort of different domains that have computational needs, and there are these hundreds of thousands of libraries that are supporting sort of that need under beautiful abstractions, which are fast and easy to use. But there's a big problem with these libraries, which is that these libraries don't scale to application needs. So here's a simple example from this class domain, where sort of you deal with matrices and vectors and higher order concepts. And in this particular example, I have x and y vectors. I'm making the outer product of them, scaling it with alpha, a scalar, and then adding it back to the matrix A. If I want to run this computation today on the Apple M1 chip, I basically have two options. I can either use Apple's Accelerate library or the ARM developer tool. Both these sort of libraries support this exact function, meaning there's some function in there somewhere that you can call, which takes three arguments, x or four arguments, x, y, alpha, and a, and returns the new a. So this is great. It's heavily optimized. Everything is inside it. You just have to call it. And the performance is pretty great too. Actually, both the libraries are pretty competitive on that sort of particular application. But what happens if I slightly change this application? If I scale A by a scalar beta before adding it by n, now this particular function is not available in Accelerate, but it's available in R. So what I'm forced to do in Accelerate is actually break it down into three computations, the scaling, the first part, and then adding it up, which leads to some performance loss. There are multiple reasons for why this happens, but just take my word for it that it's slower because you're doing it as multiple operations instead of one unified hand-optimized sort of implementation. The ARM developer library performs better as expected. But if I further change the application, if I make it plus B plus C, where B and C are also matrices, neither of these libraries support this application, meaning you have to break it down into a bunch of computations. And my lab mate wrote the hand-optimized implementation of that, which I'm showing here in purple, which performs better than both of them. So the point I'm trying to make here is, as these application needs keep changing, the demand sort of is not, the application, the library writers are not able to keep up with the demand. Okay, so the sort of other approach, which a lot of us compiler folks like, is to use a domain-specific language. For folks who haven't heard this term before, domain-specific language or DSLs are programming languages that cater to a specific set of applications. So instead of being very general like C++ or Python or Java, where you can write any application, these are languages meant to be sort of for specific class of applications. So here's an example of a DSL called Taco, which came out of our group. And this particular sort of language has its own syntax where it takes as input that expression that we wanted to run. When you pass it to Taco DSL compiler, and it produces some very highly optimized code that sort of combines all the operations and produces one implementation. And this is fast as expected. Now, if I change this input a little bit, it gives me a different output and so on, which is optimized for that particular expression. And this is great. The right-hand side code is hard to read, but it's not meant to be.
I can't resist. You might want to change the name Taco.
Oh, it's very unfortunate timing for that.
Terrible time.
I hope the USA doesn't go after
Your
me for this,
funding,
but
Saman, your funding.
My part, yeah, I'm done with that.
It's already under attack.
so the output code is complex, optimized, and runs very fast. So that's great. But there's a problem with these DSLs too, in that writing these DSLs is hard. Here are some of the DSLs that came out of our group in last 15 years, and you can see that these are really big sort of implementations. The dynamics of DSL, for example, is about 350,000 lines of C++ code containing a parser, an IR definition, transformation, analysis, code generation for different backends, and so on. Writing these DSLs is hard, and this is not something we should expect from library writers who are used to writing code for their domain. Okay, so to just summarize the problem that I mentioned just now, there are basically trade-offs in what we're trying to do here. If you take the approach of writing hand-optimized implementations, you get really good performance because developers have spent a lot of time trying to optimize it. They are relatively easy to implement because you have to implement a few functions that are very useful, but they're not very general, meaning you can't sort of support all application needs. If you write a very general library that has small functions that you can compose and then get all your applications, it's obviously general. It's also easy to implement, but you sacrifice performance in the process. And if you take a DSL approach, you get high performance and generality, but this is extremely hard to implement. What we ideally want is something in the middle, which is easy to implement, high performance, and general. And so today's talk and these four different sort of independent but sort of connected line of work that we have done, I'll explain how to build such systems easily, add optimizations, transformations, debug the code that you have generated, and go through some case studies. Okay, so we wanted to understand why these DSLs are hard to implement. And fortunately for me, I came to Saman's group in 2018, and I was surrounded by DSLs. There's a lot of DSLs that came out of our group targeting very different domains. And I started working on this one particular DSL called Graphic, which has this sort of programming model where it takes two different inputs, algorithm description, where you specify what you want to compute, and scheduling description, which specifies how you want to optimize that or how you want to generate code out of that operation. The compiler then mixes both of these two and then generates low-level code that runs on CPUs, GPUs, and different accelerators. If you look at, so this scheduling language, by the way, is very specific to Graphic because it has things like iteration order, the iterating through vertices and edges, it has load balancing, and so on. You don't need to understand that, but just get the idea that it's telling the compiler how I want this code to be optimized. If you look at another DSL that I mentioned before, Taco, it has a similar model. I had shown the sort of algorithm input before, but it also has a separate scheduling input, which specifies what optimizations to apply, and it generates code. Halide, the popular DSL, follows the same pattern. I won't go through it again. So the obvious question I asked myself back in 2018 was, why do we need n different compilers to sort of target n different domains? This is where a lot of effort is being wasted. So let's look at this sort of problem again in a more abstract way. We have a full DSL compiler that is for the full domain. It takes two inputs currently, algorithm and schedule. But what's inside this compiler is domain knowledge. This domain knowledge tells the compiler what the abstraction is, what optimizations make sense for it, when to apply it, how to generate code, and so on. And that's what makes these compilers unique. So what if we make this domain knowledge into a third input for the compiler? We won't need to build too many compilers now. We just have one generic DSL compiler, which takes us input the domain knowledge and then generates code. So okay, this is a great start. But what really is this domain knowledge? What does this even look like? Is this code? Is it optimizations? What is it? Okay, so let's look at an example again from the Graphic domain. This is a DSL targeted towards graph applications, meaning you have applications like shortest path, breadth first search, connected components written in this DSL. A simple example here shows different abstractions in the language. So we have some types like edge set, which holds a bunch of edges to process, and we have vertex set, which holds a bunch of vertices to process. And then there's an operator call at the bottom. This operator call is a bit long, so I just break it down. It says start with all the edges in the set edges. From those, keep those edges that are originating from the active set, meaning the source vertex lies in this active set or is part of this active set. Then keep those edges from those that where the destination satisfies the not visited property. The not visited here is just a user-defined function which accepts a vertex and tells you whether to keep it or not. And then on the remaining edges, apply the function update edge. Now, this update edge function is also shown here. It's a user-defined function which takes two parameters, the source and destination, and in this particular case performs the computation, new rank of destination plus equals old rank of source. So if I've written applications before, you might recognize this as the PageRank application. Specifically, this is like a variation of PageRank delta because you're not processing all the vertices and edges at every graph. Okay, so now if you go to a graph expert and ask them, how would you implement this? How would you sort of actually execute this logic? They would present you with three options. The first option is this, where if the set of active vertices is very small, meaning it like a very small fraction of the vertices are active in the set, turns out the best strategy is to actually parallelly iterate through all the vertices in that set. Then for each of those vertex, serially iterate through its neighbors, check if the destination or the neighbor satisfies the not visited property, and if it does, apply the function update edge. This is great because you're actually able to get a lot of parallelism out of those active sets without having to go through all the vertices. You just go to the vertices that are active. Turns out if the sort of set is medium dense, meaning a large subset of vertices are active, but not all of them, the best strategy is to actually parallelly iterate through all the edges in the edge set, then check for the source property, check for the destination property, and then apply the function. This is better because you actually end up getting more parallelism out of it. Notice that you're actually parallelly iterating through the same source on multiple threads, meaning you're getting more parallelism out of it. And finally, if a large fraction or a very like a majority of vertices are active, Turns out the best strategy is to actually first transpose the edge set, meaning flip the source and destination, then parallelly iterate through the destinations, check for the not visited property or the destination property. Then the ones that satisfy those, serially iterate through the sources, check for the source property, and then apply for it. This is better because you actually end up eliminating a lot of vertices which are not satisfying the not visited property. So you get more work efficiency out of it. Furthermore, the update edge function itself is also compiled different. In the first two cases, if you notice, it's multiple sources are being assigned to sort of different threads, meaning two sources that share the same neighbor could simultaneously try to update the destination of new rank of destination, which means you could have race conditions. And to ensure correctness, you are forced to insert an atomic axis. But in the last case, since you are assigning a single destination to a single thread, we can be sure that no two threads will simultaneously update the same location of new rank of destination, and we can eliminate the atomic axis, improving performance. This one slide is what I call domain knowledge, because what I'm trying to explain here is what abstractions and what optimizations make sense in this graph domain. This particular variation would not be possible for any other sort of for loop or any other program that you write. It's specifically meant for a graph domain. And there are sort of a lot of caveats in it. You have to be careful about performance, correctness, and so on. And those things is what encompasses the domain knowledge. Okay, so what would you like? What would the library writer or the domain expert do if they were supposed to, or if they were asked to implement this apply operator? What they essentially do is just write a big giant if condition, and inside those if conditions, dispatch the right versions. Now, this is great because the first observation here is domain experts actually already know how to write these optimized libraries. They have thought about this before, and they have implemented these libraries before. But there's a problem here, which is that these conditions are now being checked at runtime. In this particular case, the check is at the outermost level, so it doesn't actually cause performance degradation as much because you check it once and then you run the majority of the work. But let's think about the update edge function. That also has a similar check inside. And this function is being invoked on every edge in the sort of graph, which could be billions of edges in typical applications, and that's going to cause some slowdown. So ideally, we would want, based on sort of compile analysis and inputs, to generate a version that's specialized to those particular cases, instead of having to like check these conditions accurately. And that's what a DSL compiler can do for us. So we sort of spend some time trying to understand and sort of figure out what the typical workflow for developing a DSL compiler is, so that we can figure out how to simplify it. So the first step is usually to get abstractions, which I've shown before, and domain experts already know how to do that. The second step is to figure out domain-specific optimizations. So like the step that I talked about before, how to compile a specific apply operator, and so on. And the final and the most sort of difficult step for domain experts is to generate code. To implement some sort of parser, IR, code generation, transformation, and so on. And that part is hard. Like I said, the domain experts know how to do these first two things because they do this all the time in the libraries.
So, question?
Yeah.
Which domain experts are you talking to here?
So physicists, chemists, anyone who is used to writing high performance code.
I mean, but there's a lot of domain experts who aren't used to writing any kind of code.
Right. So I actually categorize domain experts into two parts. There is within each domain, there's a few sort of select few who know how to write high performance code, and they are the ones who usually go out and build these libraries. And then there's a larger community that consumes that library. So when I refer to domain experts who can write high performance code, I mean that library development. So like, for example, in the blast example that I showed before, someone wrote that library. They might not be a compiler expert, but they know how to write high performance code. I'm referring to those as domain experts. Okay, so
that's the target audience for the transfer.
yeah. There's sort of like three users. There's me, who has developed the system. There's a second user who is a domain expert who's used to writing high performance libraries. And then there's the end user who will consume those libraries and then DSLs now to actually implement the applications. Okay, so we want to build a system that can automatically sort of take those libraries and make DSL compilers out of it. And to solve this problem, we made a system called BuildIt. A very high-level sort of marketing pitch for BuildIt is that it automatically turns library code into compilers. A more sort of technical description of BuildIt is that it's a type-based multi-stage programming library in C++. Now, there's a bunch of keywords here. I'll explain some of them right now. But the first thing I want to explain is what is a multi-stage programming library. This means different things, but I'll explain what that means in this context. So let's start with this typical single-stage program. In a single stage program, you write some code, might be C, C++, Python, whatever. You compile it with your favorite compiler like GCC or Clang, and then you get an executable. You run this executable with some input, and you get a final output. This is a single stage execution. BuildIt generalizes this to sort of multiple stages where you start with some source code. You compile it again with your favorite compiler like GCC or Clang, and then you get as output an executable. At this point, you specify parts of the input. So notice that the input is cut into half. You provide parts of the input, and the output of this execution is source code again, which is specialized for those inputs. You can compile this code again with your favorite compiler, get an executable, feed in rest of the inputs, and then get the final output. So breaking down the process of compilation and execution into multiple steps. This can obviously be generalized to more than 2 steps, but for this thesis defense today, I'll only focus on 2 steps. Okay, so what does this look like? How do you sort of, the second part of it is the type-based part.
Can you go back?
Yeah.
I missed the slide. Tell me again.
Sorry, this one is describing the workflow for what a multi-stage execution means in this context. We start with some source code, C or in this case it's C++. We compile it with a compiler like GCC or Clang. There is no modification, it's standard compiler. You get an executable out of it.
Yep.
At this point, you feed in parts of the input. So just a subset of the input. And then you get as output a program that's specialized for that part of the input. So the key point here is that the output of it is a string, which is source code for the next stage. There's an explicit sort of multi-staging happening here. You compile that source code, feed in rest of the input to the executable, and then get the final output.
But this is, at this point, we're just doing the standard stage compilation story.
Yep, this is standard stage multi-staging, but with the caveat that it's explicit, meaning that the output of the first stage is source code instead of being some compiler intermediate. And I'll talk about why that might be later. I'll also show some examples which might make it clear. Okay, so let's go ahead. Let's talk about the type-based part of it. So in BuildIt, the types of your declared variables sort of decide what stage that particular expression or variable would be evaluated. So the BuildIt library in this case just adds 2 new type templates, dynamic var of t and static var of t. Anything you write with static var of t is completely evaluated in the first stage, and anything you write with dynamic var of t is produced as it is. So here's a simple example that we use a lot, which is of the power function. It takes 2 inputs, base and exponent, and returns base power exponent using repeated squaring. Now, in this case, what I've done is I have declared the base to be dynamic of integer, and I've declared the exponent to be static of integer. So now, since the control flow like the while loop, the if condition are all dependent on the exponent, which is static, it's completely evaluated. And what you get is an output program that's specialized for that exponent. Notice that the exponent static value 15 is provided as an input to the program in the last statement, which is a constant in this case, but it can be any program value. It can come from an input, from a file, or whatever you need it to be. And now, if I want to change the specialization slightly, I can change the exponent to be dynamic and the base to be static. And the output program now changes to this. There's no other changes in the code. It's exactly the same, just the types have been swapped around. And now in this case, because the exponent is dynamic, the control flow like the if conditions while loop are preserved as it is, and the generate code looks like this. The base should becomes a constant somewhere in the code, but that's fine. It's not. I'm just demonstrating that changing specializations is as easy as just swapping around some types. Okay, so how do you implement sort of a programming model like this that we have in mind? A sort of a typical approach that most compiler experts like us would take is to implement a static compiler based approach. Meaning you implement a special compiler that can do this stage execution for you. Let's look at how that would look like. So you start with some source code and you have your fancy new compiler that can do staging. You have to add a new custom parser first. Maybe not in this case, but in some cases you might have to add if you have new syntax. Then you have a new IR that can represent these 2 different sort of stages and execute part of them. Then you have the main part of this new compiler is this partial evaluation interpreter inside the compiler. And then you have a specialized code generation phase that can generate the code for the final output, which will give you the code. Now, the big problem here is that, first of all, this is a lot of work to implement. But second, this partial evaluation interpreter, which is at the heart of this sort of new system, dictates what can be done and what cannot be done. So any rich features you need to have will have to be implemented in this partial evaluation interpreter. Let's look at, and this approach sort of is taken by the C++ templates and const expert system, where the compiler internally evaluates those code to completion and produces some new code. The problem with this is you're limited by what the interpreter can do. So for example, C++, the language itself has a lot of nice features like mutations, external library calls, heap allocations, IO, pointer and direction, loop, and so on. But if you look at templates, the static evaluation part has none of these, which means you're restricted to write a very subset of the language, which is not as expressive as it can. So that approach, let's keep it aside for a minute. Let's look at the other approach, the other extreme, which is to take a complete execution-based approach. So let's take an example of, say, something like TensorFlow, where you don't have a special compiler, you just have a library where you define these placeholder types like tf.placeholder, tf.int, and then you can add expressions based on that. So you can say c equals to a plus b, and instead of executing c equals to a plus b, it will produce c equals to a plus b. And now you don't have to be limited by what you can do because the language itself is running, like you're running full Python. You just have to overload the semantics of what it means to do a plus and assignment. The sort of small caveat here is that control flow becomes difficult in most languages because these host languages don't allow you to overload this control flow. So what you're forced to do is write these tf.conditionals and tf.while, which look a little weird, but also have different semantics. So for example, if I write the power example that I had shown before, this is how you would write it in TensorFlow. Notice that the tf.while is not a statement anymore. It's just a function call that returns the state of all new sort of updated variables. And this is bad because you have to not only make local changes to your program, you have to rewrite your whole program in a new sort of paradigm of like this functional kind of paradigm. So this is not great either because when you start working with big applications, this becomes tricky. There's a third and hybrid approach that people have taken in the past, which is actually sort of solves both the problems. What it does is it preserves the syntax of the language by taking a compiler approach that first sort of converts and goes and rewrites those applications to sort of replace the normal if condition and the while loops with these special constructs like tf.conditional or tf.while, and then execute it normally. So you get best of the both worlds in some way because you have a compiler approach that can preserve the semantics, and the execution system gives you all the features the language has. And this is fine. This is an approach that's taken by lightweight modular staging in Scala and then also MetaCaml. But all these three approaches that I discussed so far have a major drawback, which is sort of explained through this example. Imagine if I had taken the same approach of adding sort of this BuildIt if, either through compiler changes or manually written BuildIt if. There's a big problem here because C++ is a sort of imperative language. You have side effects. Now, in this case, I have two variables, x, a static variable, and dynamic variable y. I'm branching on the dynamic variable y being greater than 5. And then what I've done is I've provided the if part, the then part of it as a lambda, and the else part of it as a lambda. So now what the execution system would have to do is go and evaluate the then part, extract the code for it, go and evaluate the else part, get the code out of it, and stitch it together to get an if condition. But what if I have side effects on x in the then part? Those side effects will now leak into the else part, which will give me wrong code. Even though those branches, only one of the branches is supposed to execute in the program, because I have to execute both the sides to get the complete picture, I have to evaluate both of them and the side effects are leaking. And this sort of problem we want to completely solve, while also not requiring special context. So how does BuildIt work then? Well, how do we solve this whole problem? Let's take it step by step. Let's look at static variables first. Static
Can you go back?
Yeah.
Problem again? I said, what's the problem?
Oh, the problem here is that x is being updated on the then branch, but its side effects are also seen on the else part, which should not happen. X equals to x plus 1 is happening on the then part.
And that's happening because you're getting both parameters.
Because the sort of system needs to, this BuildIt if is internally going to execute both the lambdas.
Why does it do that?
Because y is a symbolic variable, you don't really know if y is greater than 5 or less than 5. So at first stage execution, you can't decide whether the else branch should be executed or the then branch.
This just sounds like a pub.
No, this is what exactly will happen with any system that uses these special constructs for partial evaluation. This is like a limitation. I mean, it's a known limitation sort of bug really. It's because your program is going to have a bunch of control flow paths diverging and converging, and to get a full picture, you have to execute all of them. And in doing so, you will have some side effects leaking from one side to the other.
Why don't you keep
I
going?
can show some examples that like get handled better.
No, so actually, this is not what you did.
It's not what we do. This is a hypothetical. If we had done this way, this would have been. Okay, so let's come to our solution. Let's talk about static variables first. Static variables are just like normal variables that are executed in the first stage, which means they have a concrete value. So static variables of t is just a wrapper around a t. It just has an internal t of val, which implicitly converts to t whenever required, and behaves exactly like t. It has some special constructors and destructors, which I'll talk about later, but that's not relevant right now. The idea is static variables are just wrappers around t, and they just behave normally. Dynamic variables are special because we want to generate code for them. They don't actually have any concrete value stored inside them. They're just symbolic placeholders for what a value would be in the second stage. And what we have done is we have overloaded all the operators like constructors, destructors, plus, star, assignment, function call on these types, so that whenever those expressions are executed, they'll produce the same exact expression instead of running it. So when you say x plus y times 2, it produces var0 plus var1 times 2. The names are not the same because C++ doesn't let you get the names of the variable. You only know that there is a variable of this type, so we generate names by ourselves. But the semantics are preserved. And then everything is overloaded, produces the same expression. When we come back to the same problem, which is what about conditions and loops? What happens if you have control? We can't overload that in C++, but this is where sort of our first contribution comes in, which is what if we start like exploring this control flow every time it happens. So if you ever put a dynamic variable or any sort of custom type inside a if condition, C++ semantics will automatically try to convert that to a Boolean to see if it's a true T value or a false T value. And the way it does that is by sort of calling this explicit cost to bool operator. So we overload that. That's our way of getting a sense of when an if condition is happening. And now what we do is we try to return true and false separately to explore all the possibilities. So let's look at an example here. We have two variables when declared x equals to 0, y equals to 1. So that produces the statements x equals to 0, y equals to 1. Then the execution reaches x equals 0, which produces x equals 0. And then the explicit cast to bool operator is called. So the first thing we do is leave a placeholder there, or sorry, not a placeholder, a marker there saying, okay, this is where some sort of exploration is going to happen. And then we try returning true from it. Notice that the return value of dynamic var of t operator bool is a bool, not a dynamic, which means it has a concrete value. So return true from this, and the execution will continue from there, produce y equals to 2, and sorry, y equals to 2, and then z equals to y afterwards, and the program terminates. Now, but we haven't finished the whole exploration yet, so we restart the program again. We say, okay, what happens if we continue the execution at that point, see the marker, and then at this point return false. So the execution continues to y equals to 3, we get z equals to y, and then we get these two traces. Now what it does is it merges these two traces based on where we had separated, and then puts an if condition. And then it further sort of like collapses everything comes after that's the same, and you get a program sort of AST like this, which you can then generate code out. And this sort of, at least maybe there's a sort of, you can get a hint of why this solves the problem that we saw before, which is executing everything from the beginning. So the side effects are contained to the side that was executed in that particular.
So, I mean, the number of paths is potentially exponential, right?
Yes. So if a live implementation was done, and if you have n number of branches one after the other, you would have a path explosion problem. But BuildIt has sort of this memorization capacity built in, where if you see sort of the same program statement that we had seen before, it kicks in and then like sort of recovers the code from other paths. And that brings the complexity down from exponential to actually polynomial. You only require linear number of runs, where linear in terms of the number of state if conditions you have after here. And that the details about those are in the paper, and we show sort of like a empirical and some proof of why it is.
I mean, assuming some structure to the graph, like that you have some joins or something. Because I can imagine that there's pathological graphs where it would be exponential.
Right. So if you have nested if conditions, then yes, that's going to have exponential explosion anyway, because the output program is of that size. But the pathological.
But I mean, the output program is not of that size. It's because you're doing symbolic execution that you have a problem, right?
No. So
I mean, what it means, you have lots of. If you had values, then you would just explore one of the paths. But you're trying to get a data structure to represent all of the paths.
Right.
It's much harder.
But we never actually construct all the paths. We only construct like once a path collapses, like once the path join, that's one statement after it. We don't have to maintain all the paths.
No, I understand with the joins, but I guess you're just basically assuming that these modules may have small exponents, basically. you may have like 5 nested ifs, and then inside of a module,
Yeah,
and then you're going to have 2 raised to 32.
absolutely.
And then you have a join, and then you have another 2 raised to 32, but you don't get to the 2 raised to 64.
Exactly.
Right?
You get
Like,
to the
or maybe it's not 2 raised to 32, it's 2 raised to 5. Double exponential.
which is actually required because your output program also has 32 sort of like paths being generated, right? And that's required because they could potentially be different. And if they are the same, they get collapsed together. So yeah.
You also do this for loops.
Yes, I do. Yeah. So that solves the problem of if conditions at least initially. But what about loops? There is really no way to discern loops from if conditions because all you're again doing is throwing a dynamic variable into an sort of a Boolean sort of expression and try to check if it's truthy or falsy. So let's do the same exercise again, but with a small change in that every statement we generate, we're going to annotate it with this thing called a static tag. To give an intuition of a static tag is it's sort of an identifier to tell you where this code came from and what was the state of all static variables at that point. So it's a concatenation of where you are in the program and the state of all the first stage variables concatenated together. Okay, with that, let's start executing from the beginning. You get x equals to 0, tag 1, like after defined as 1. Then you get x equals 42. And then this is where the exit cast to bool operator happens. We return true and start the execution ahead. We get x plus plus. And because we return true, the execution goes back to x less than 42. At this point, we see that the static tag is exactly the same because it's coming from the same place in the program. And all the static variables are trivially the same because there are none in this program. So now we say, okay, I can guarantee that at this point, no matter how many times I run, it's going to produce the same exact program from this point. Because we are in the same place and all variables with the concrete values have the same value. So what we do is we stop the execution and put a backage instead. We say, okay, this must go back to where it came from. Then we restart the execution again and do the false part to get the z equals to x with the if condition. And this is a rudimentary sort of loop. We have if and go to going back. Now what BuildIt does is in post-processing massages this into a while loop or a for loop if we can consult out of it, and then we get code like this. Does this make sense?
What are your criteria for how you specialize functions? Like you're specializing based on dynamic values?
We are specializing based on static values. Because you're evaluating fast. There's no specialization happening here because it's producing the same code as what.
Oh, okay.
You could specialize this by putting conditions on static variables in the middle, which would be conditionally evaluated concretely based on what the input was.
Oh, okay. So this part you're just like taking a dynamic space the program versus generating the source code. That was
So
there
this
is the point.
Yes, no, there's no access to source code. It's just
Yeah,
executing
you're
it.
reverse engineering.
And in doing so, you could have static variables being assigned and evaluated and checked in the middle, and those effects will completely happen immediately. There is no special sort of like second stage where you partially evaluate the static part of it. It gets evaluated as part of the execution because remember, static of t is just t. So if you say if x is greater than 5 and x is static, it will actually check if x is greater than 5 and produce the code that was inside that. Okay, so let's go back to the power example that I showed before, just to give us sort of a final rundown of how it works. We have this power function with the sort of exponents. In this case, I'm doing the exponent dynamic and static base. Start executing, I get this code from the first run where we return true for both the while and the if execution, and then there's a loop back edge. We start the execution again for the other case where we get true in the while and false in the if, which gives us this code. And finally, the third run, which returns false for the while loop itself, just produces this code. And now first and left to get merged together to produce an if condition. So that's what we get here. And then finally, this also gets merged into it, giving us this if condition with a back edge, which gives us the while loop. And finally, we produce code out of this. So
how did you implement this?
it's all implemented as a C++ library. So BuildIt just defines these two types called dynamic of t and static of t. And all the operators on this dynamic of t are overloaded, which means that every time an operation happens, we get a feel of where we are in the execution. I think Saman is a nice analogy for this, which maybe I'll repeat here, which is imagine you are in a maze. And if you're trying to solve the maze from top up, if you have a complete picture of the maze, you can solve it trivially. But if you're inside the maze, you can't see the whole maze. But what you can look at is sort of where you are in the program, and you can sort of like start exploring different paths in the maze, leave some markers around to say, okay, I have taken this path, I came back from here, and so on. And then by doing that, you sort of get a complete picture of the maze. So the equivalent of the maze here is the program, and the equivalent of feelers is the operator. So BuildIt only sees the execution to these narrow window of operator overloading, but uses that to construct a whole picture of the program and reconstruct the control flow from scratch.
All right, let's say if I just wanted to do sort of a very generic implementation of this algorithm, starting from my own language, my own pilot, all this kind of stuff. Would the algorithm be any different?
The algorithm would be exactly the same because the key idea here is re-execution. If your language provides support for looking at control flow, you could simplify a lot of the logic. You won't have to do this explicit cast to pool, but you would still need this re-execution part of it. Because unless you execute a program end to end for a particular sort of sequence of conditions, you can't get a correct view. If you try to like break it down into smaller programs and explore them separately, you get that leaking of side effects on static variables.
How much of the contribution is figuring out how to make C++?
I would say, okay, not in this. A majority of this presentation today is not focusing on the C++ sort of contribution. It is focusing on the algorithm. But there is a lot of like sort of effort that went into making it more ergonomic. Like how do you do custom, making it more ergonomic? So like if you have custom type like a struct, how do you make sure the dynamic of struct just works without making too many changes? Because we want ideally to take code in the original sort of library and copy paste it. And that requires a lot more sort of C++ hacks into it. But the core algorithm is pretty simple and it sort of is what I'm covering today here.
So I should be looking at this as an extension of staged compilation to deal with something. Is that
Sorry, for the last one.
an extension of staged standard staged compilation story to side effects? Is that a fair characterization?
I can't hear the last part.
So it's an extension of staged compilation. Work with programs that have side effects.
Yes.
Is that a characterization?
That's
what the claim contribution?
yes. Extension of multi-stage execution for languages that have side effects and control flow both. Because if this was a functional language, the problem was trivial. You just have a special if condition which returns an if condition, and you don't have side effects on first stage variables, just flow through as values. That's perfectly fine. You need two things. One is control flow to exist in the language and to have like side effects on first stage variables.
So what if in functional languages you have exception, right? How do they deal with that?
So in this case also we have exceptions. C++ also has exceptions.
Sure, we're talking about.
You mean like exceptions that cause side effects or exceptions that
Some sets of side effects, right? If I'm executing both branches of an if, one of them exceptions, then my project is terminated.
right? So in that in the hypothetical implementation in a functional language, you would have some sort of a construct that can say expresses the if condition. You would say like condition and then else and then expression. In that you will catch the exception. So you won't sort of throw the exception ahead. You will keep it as, and then in the generated code you would put an exception like throw there. Like if one of your else if a then branch throws an exception, you'll catch it there, and in the generated code put a code that throws the exception again. So that way you will constrain that exception to that branch. You won't let it leak further up. Okay. Rest of the time I'll go ahead because there's a bunch of material to cover, but we can get back to it.
Yeah.
Okay, so let's go back to the original problem we started from, DSLs, and this library that the library expert wrote. Now, how do we make this into a compiler? The answer is very simple. You just declare those things that control which version to run into static variables, and then you keep the actual data which controls the vertices and the edges as dynamic. And now when you execute this program, the same program that the developer had written before, you either get this version or this version or this version. Funny enough, the update edge function also gets specialized directly. You don't have to get sort of like this condition being checked again and again, and you get what you want. Just by changing type of those variables, you can get a compiler out of it. So this solves our first problem, which is how do you do basic code generation? How do you specialize the library that you have written? But the compiler experts among us would say compilers are more than just generating code, right? Compilers are analysis, transformation. You don't want to like, you want like analysis that's go across operators. How do you do that? So this next line of work will describe how to sort of build classic data flow analysis and other analysis into this new system and what kind of performance gains you can get out of it. Okay, so let's look at the same graphic example before and the same update edge function before. We want the user to write this. We don't want the user to write that if condition to say whether it's small than 2 atomic or the version 2 atomic. We want that atomic to be inserted automatically. So how do you figure this out? Because it depends on how this update as function is being called. If it's called in one of those first two conditions, it should have atomic. If not, it should not have atomic. So in the before I started BuildIt, there was a graphic compiler which we worked on, and that solved this problem by using data flow analysis. So for each of these vertex variables, you can keep track of a property about them, whether it's shared, independent, or a constant. By shared, I mean the same value for that vertex is assigned to different threads, which means that vertex is shared by multiple threads. It's independent, meaning that it's only one thread is responsible for that vertex, or if it's a constant, as in it's literally a constant. And if you track these properties about every vertex variable in your program, and when you use it at a sort of index like this, you can figure out whether to use an atomic or not. But this requires a lot of compile analysis and transformations, which library experts are not used to doing. So how would they do this in our system? We start by defining this vertex type that controls this whole execution, and it has two members inside. It has a dynamic variable of int called vid, which will actually hold the vertex id at runtime, meaning it's a placeholder value now. But it statically tracks this property about it, whether it's shared, independent, or a constant as an either. Okay. And now what the library developer would do is every operator they write with this vertex type, they can update these properties. So for example, this plus operator, if you have a vertex that's sort of independently assigned to different threads, it will stay independent if you shift it by a constant. In all the other cases, it might now start sharing. If you add like two vertices to each other, they might now start sharing. So we write this domain specific if condition that updates those properties, which in compiler terminology is called a transfer function, but without understanding what a transfer function is. And then when you actually use those values, you can branch them. So the right way they define the arrays that can sort of hold properties about vertices, you can overload the plus equals to operator and check, okay, if the index that is indexing into this array, is it a independent one? Then do a simple sort of plus equals to, otherwise do an atomic access.
Can you go back to the previous slide?
Yeah. The basic idea is this type where we are packing together a dynamic variable and a static variable that tracks properties about that dynamic variable in the first stage. And all operations on that dynamic variable sort of update the static friend of it.
Right. This is. Are you saying this is data flow analysis?
This is towards data flow analysis. This automatically gives you data flow analysis because first of all, you write these transfer functions as just updates on those static variables. And then the system by its design itself takes care of the rest of the part of it. So for example, okay, I'll give you an example. As the sort of execution flows, these properties will progress ahead. But if you ever have a back edge that goes back to the old sort of execution, remember that BuildIt tracks values of all static variables. And if they're not the same, it won't put a back edge. Meaning, trivially, it will unroll the code till you get like a steady state execution. And that satisfies all the properties required for a static for data flow analysis.
Let's say a merge operator.
A merge operator is also implicit because anytime the static values become the same, the static tags we add will collapse and they will produce the same code. If you need to manually sort of make them like merge, you could just have a function call in the middle where it says merge all the vertices at this point. And the user can, the library developer can just insert a function call where it says trivially set the static property to a certain sort of combination of these two values. If you want to like sort of collapse the execution after that point.
So the domains that you have is values. You don't have lattice.
Then this is the lattice. In this particular example, the shared, independent, and constant is the lattice. Shared is the most conservative. Independent is the most like the optimistic value.
How do you get shared?
How do you get shared? So at any point, if you can never decide whether it's going to be independent or not, it becomes shared. I'll show an example of where it starts out. How do the values get started out? And then that will make it clear. Okay, so then let's look at an example of how this can be used. When the library developer is writing this implementation, where say they're serially iterating through source and destinations, before calling the user supplied update edge function, which could be any function, they would just set the source and destination access to be independent because they know that there's only one thread that is running at this point, and it's going to so each thread is going to run one after the other. Each vertex is going to run one after the other. Now, when this property flows inside the update edge function, and the new rank of destination is being indexed by it, we see that it's indexed by a independent variable, so you get this code out. But if you, when the library developer is writing the implementation of the parallel outer loop, they would mark the source to be independent because you're still assigning a different vertex to different thread, but the destinations can be shared. And they know this for domain knowledge. They would mark the destination actions to be shared. Now, when this value flows inside the update edge function, the new ranks of destination is being indexed by a shared, potentially shared value, so it will produce an atomic access there. And in the final case, where you sort of take the transpose and run parallelly through destinations, the domain expert knows that you're iterating parallelly through destinations, which means each destination is assigned to a separate thread, so they are independent, but sources can be shared. And when that flows into the update edge function, you still see that the destination is being indexed by independent value, so you get the non-atomic version of it. And this sort of the specialization combined by tracking properties about dynamic variables using static variables gives you the whole data.
Does operator square bracket, like that thing creates that struct from before, the combination of the like dynamic variable and static variable, or
No, that's just the definition of the vertex type. So this is not part of BuildIt. This is the library developer writing this on top of BuildIt, where they would define this struct vertex, and that struct vertex internally would have a VID dynamic, which will just hold the actual vertex ID, and a static like enumeration which will keep track of the properties about that VID. And then the end user will come along and write a program like this, which will then use those vertex types. And in their programs, those values will automatically be tracked. Okay. So
where does the atomic add come in?
So that comes in from here. Here. So when you're defining that, again, as part of the high performance library that they're writing on top of BuildIt, they'll also define, say, this array type, which will define which hold values like this new rank and so on that we saw before. And in the plus equals to operator on that array,
Whoa.
it was not was you would put a definition like this. You would say if the index that you're indexing with is a independent value, then do a normal plus equals, otherwise do an atomic. And because BuildIt evaluates this completely, since static variables are concrete values, only one of the code will be generated. We'll get back to this again if there's more questions, but let me just quickly go through this now. Okay, so apart from the data flow analysis, we also added support in the system itself to basically annotate loops like this with any sort of pragmas. You just call a function called builder annotate, which is a first stage execution function, which just takes a string as a parameter, and if that string starts with a pragma, it will preserve that pragma as it is. So you can start mapping loops to threads in CPUs now. And similarly, if you have a loop nest like this with two-level loops, you can annotate that loop with a CUDA kernel string, and that will the BuildIt will automatically go and convert the body of that loop into a CUDA kernel, and then get the launch parameters out of the bounds of those loop and insert a call at the place where the original loop was. It will also take care of moving data between the kernel and the CPU as required. And this gives us basic primitives to start mapping computations to CPUs and GPUs, parallel CPUs and GPUs. But then you can build very complex abstractions on top of it. You can write libraries that can load balance or assign different threads and so on, which we have done. And that gives us the performance speed up where we re-implemented the graphic GPU compiler that we had worked on before using this new system. And we evaluated on this 5 different applications and 9 different graphs. And on all of them, it performs equal, if not better. So here the graph is showing speed up over a normalized runtime as compared to the original graphic compiler. So the lower is better. Lower than this one line is better. So all these cases better. In some cases slightly slower, but in most cases it's equal or better. And then the key point of this is we were able to implement this whole thing in just 2021 lines of C++ code, as opposed to 23,000 lines of C++ code for the original graphic compiler. And the reason for this is this new compiler doesn't have any IR. It doesn't have any sort of code generation space. It doesn't have any parser. It just has the domain knowledge that we talked about before, encoded as a C++ language, which is also very similar to what a typical graph library would look like with some type.
So when I can't give a graph program to your compiler. I've got to write it.
And the syntax is different. It's an embedded C++ DSL. We have preserved it to be very similar. So instead of having like the func notation that the Scaffold syntax has, this one now has like a normal function defined in C++. It looks very similar, but like the syntax, exact syntax is different. Okay, so I just covered like some basic code generation, some examples of analysis you can do, and some speed ups you can get. Let's talk about another aspect of a compiler, which is very important, which is debugger.
Wait, what time you skip that to the
I can quickly go through it. I'll just go through it in 10 seconds. Okay, so the big problem here is that we have two users, someone who's writing a DSL and someone who's using the DSL. The DSL user comes in, generates some code and tries to execute it and they get a bug. The problem is that when they attach a debugger to the generated code, what they see in the debugger is the generated code out of the compiler, not the code that they wrote. And this is hard for them to debug. Ideally, what we would want is some sort of communication, sort of mapping between them, so we can tell the user what the original program they wrote was and why there's a bug. So to solve this, if you try to solve this in traditional techniques, you have to re-implement some modifications to GDB or LLDB or WinDebug, which are really large code bases, and you can't expect domain experts to do it. But the approach that we took is sort of implement a system called Detox, which in a very simple sort of high-level overview, it's a generic library in C++ again that you can add to any of your existing DSL compilers, so not written necessarily with BuildIt. And it gives you an API to insert sort of domain-specific debugging information as part of the generated code. And then when you attach a debugger to the generated code, you basically have these extra commands like xbt and xlist, which are similar to GDB commands that let you see the extended debugging information, so the DSL source code and so on. And all these things have been implemented without a single line of change of code to the GDB debugger itself or the library. So you can just like, I mean, the libraries, sorry, the compiler would have been modified to add those function calls, but the debugger itself stays exactly the same. But furthermore, we applied this system itself to BuildIt, meaning what we have done is in a BuildIt execution, all static variables and the original source code is tracked as detox debugging information generated alongside the source code. So if you write a code like this, like a DSL with BuildIt now, and if you attach a debugger to the generated code, as this external debugging information, you can see the original source code from the first stage execution and the state of all static variables as part of program variables. And that lets you like get a complete view of basically what you wrote, what happened in the compiler, what code was produced. Basically improving debugging capabilities. Okay. Finally, I will talk about NetBlocks, which is one of our recent work that tackles a very interesting problem. So when we were working on some network applications a while ago, we realized there is a problem, which is you essentially have two protocols, either UDP or TCP, and they are extreme in the sense that UDP is very simple and fast, it's stateless, but it doesn't have any features. And the other extreme is TCP, which has reliability, stateful execution, congestion control, and so on. And most applications don't actually want all those features. They want something in the middle. But if you want that, you are forced to implement everything from scratch by hand. So we wanted a compiler system that can basically have these core set of features, but then all these fancy features like reliability, congestion control, routing, and so on can be added on top of it as like pluggable modules. So we wanted to build a system like this. Furthermore, we also wanted the users to be able to add their own sort of features like encryption and so on without having to extend the compiler. So this was a perfect fit for BuildIt because BuildIt lets you essentially take libraries and convert them into compiler. So we implemented like this very modular system that has in a single statement, it's a high performance aspect-oriented programming system where each of these modules are implemented through very expensive sort of virtual calls and dispatches. And the system combines all of that together to produce the most efficient code for that particular choice of modules. And here's just a list of all the modules we have implemented and the different features that they support. And you can see that a total combination of about 864 different protocols can be generated just by changing parameters and by selecting modules. But there's an interesting problem here, which is that these custom protocols also require custom packet layouts. So let's take an example. Suppose you have a simple protocol like this, which just has destination, source, and length fields for transmitting data. But now if you want to add reliability to it, or if you want to add in order to deliver to it, you have to extend this protocol to add a sequence number field into the headers. So the first observation is that packet layout depends on the features that we have chosen. Secondly, imagine you're deploying for a network which just has 4 computers. a most optimized implementation would just have 2 bits for source and 2 bits for destination, because that's enough for identifying where the packet is coming from and where it's going. But now imagine you scale up your deployment. Now you deploy for 16 nodes. You have to go and rewrite your headers to now have 4 bits each, because you have more computers to address. So the observation here is that packet layout also depend on the deployment alongside the feature chosen. So how do we solve this problem? How do we sort of do this change programmatically? Let's look at how it is done typically in a library. These headers are essentially implemented as these packed structs in C, where each member represents each one of the headers, fields in the headers. And then when you write them some application, when you write the protocol implementation with it, you take the packet buffer and then you cast it directly to the struct, pointed to that struct, which now gives you an access to directly manipulate the field. So you can do things like UDP of destination ports equals to 8080, and that goes and changes the value in the header. And this is great, but it's not programmable. Like we can't conditionally remove the checksum field, or we can't conditionally change the destination port to be shorter. So to solve this problem, we first make an observation that structs are essentially just a way to describe to the compiler how to organize data. So what if we make that process itself explicit in code, and then we already know how to stage code. So our solution involves sort of implementing this layout optimization layer on top of BuildIt. Basically, the whole packet itself is represented as this layout object, which is a very sort of modular data structure, which has a sort of a linked list for describing the fields in the headers. And then for each of these fields, we describe properties like size, alignment, offset, and so on as static values. So it's provided in the first stage. And then we implement functions like get value and set value, which now uses those constants to now generate code that automatically offsets indices into those arrays. The cool part here is that all this evaluation is done in the first stage, meaning when you execute code like this, which just creates fields and addresses them using these functions, you get code that's very optimized. You get code that's tailored for that particular choice of data structure. So if you conditionally remove this length field from the linked list, the checksum field will automatically shift up ahead, because this is described in the first stage as code instead of like handwritten data structures. And then furthermore, once you define this data structure like this, you can also start making optimizations. You can say, I'm going to add a set range function inside this data structure, which now restricts the range of values for a particular field. And then there's a complex implementation for now using that range value to index into the data structure using bit fields. But basically, when you run the same code, you just add a single extra function call saying set range of this length field to be 64 to 128, but your generate code would now look very different, because it would calculate those masks, those shifts in the first stage and produce code that's very tailored for that particular data structure. And so then we were able to take this sort of implementation and take a protocol like this, which typically has a lot of fields because of UDP, IP, TCP, Ethernet, and so on. And we were able to get rid of a lot of useless or redundant fields. Basically, for example, you have this total length field in the IP headers, and you also have a length field in the UDP header. So you can collapse them into a single one programmatically. And then furthermore, by doing data layout specialization for deployment, we can further shrink them down to like even 2 bytes in this case, which gives you still the same features as UDP, but with a very small header size. And this directly translates into performance gains. So here's just a round trip latency measurement for 10,000 requests. The two extremes are UDP and TCP. UDP being simple is extremely fast. And then here are some ad hoc protocols we created with specifically chosen features like in-order delivery, reliability, and so on. And you can notice that the performance of all these are between those two extremes. In fact, they're not just between, they're actually closer to the UDP case. Meaning, if you use our custom protocols and if you carefully select what features you want, you can actually get a trade-off between the features and the performance. Basically giving you this pay what you need kind of, pay only for what you need kind of a model, instead of having to pay for the whole TCP. The similar performance improvements are also seen in throughput. This particular case, we are evaluating a robot deployed underwater, communicating through acoustic networks. So bandwidth is really low. And by improving this protocol, especially the shrunk protocol, which is using very few bits to represent the headers, we're able to get throughput even better than the default UDP case. And so that is yeah. There's also if I have time for it, I could quickly do a demo, if that's okay.
Sure.
Okay, so the main part of this network system that I glossed over a little bit is that extending the system is also very easy. It's a compiler that can let you do features, but you can also add new features very quickly. And instead of showing slides for that, I'm going to quickly sort of show a online demo of how you can do that. So in this network system, what I've already done is for the sake of time, I've already added this empty encryption module. So the way you define it is by first creating a class called encryption module, and then you declare the hooks that you want to define. So I want to hook the operation send and ingress. And then what I can do is I can I have this empty module here, which has just defined those hooks and send and hook receive that don't do anything. Now what I'm simply going to do is implement a simple encryption algorithm here. So let's say I iterate through every byte in the field. So payload length. And then for each one of them, I'm just going to do a very super where's my escape keyboard? Escape key is broken for a second.
Might be you.
That would be. Oh, it's in the terminal. Just check this. That is annoying.
Control right bracket, maybe.
This is not supposed to. Maybe it's the
Control that bracket.
Oh, okay. I can't do this. Okay, I'm just gonna quickly try this without indentation. Bear with me. Payload of I equals to payload of I plus, like, say, some super secure Route 32 implementation, and then I'm going to I can't copy paste because my escape isn't working. We have to do this whole with just. And for decryption side, I'm just gonna do the reverse of it, which is sorry about that, plus 256 minus 13 in this case, 4056, right? And save. This.
Those,
Right. Let me just try new terminal. No, it's just the escape key. This is bizarre. And save. Even exit. That is unfortunate.
What is that thing?
That's Windows and
I think you might have to.
okay, I might have to skip this part of
Yeah, let's skip this part. This is a fun thing to do,
sorry about
but it's
that.
not.
I will get back to this after possible. Okay, but the idea was that we could just add an encryption model and the generated code will just have that logic for encryption in right place. Okay, so to conclude, what's happening with BuildIt right now? BuildIt expanding upwards. We are adding new applications and domains on top of BuildIt as we speak. So we have a Breeze domain-specific languages being implemented, which is a regular expression compiler, which takes regular expressions and generate code for that specific expression. Shim is another piece that came out of our group before, which is about compression, implemented by another PhD student in our group. And NetBlocks, which I just talked about. We currently support generation. It's expanding downwards. So we currently support generating code for CPUs and GPUs I talked about before. But we also submitted a paper recently that generates code for FPGAs from the same high-level representation. So you can now compile any of these DSLs into very different architectures with very minimal changes. And then finally, BuildIt is expanding sidewards. I just talked about Detox, which is this debugger system that automatically adds debugging capabilities. But then we also have this new system coming out called DBD, which takes existing source code and automatically adds dynamic everywhere so that you can start staging it and specializing it by making few things static. So that basically improves the user experience of migrating existing code bases into BuildIt.
How do you generate FPGAs out of this? Do you have some FPGA generation code that leads all this stuff?
Right. So it's essentially a new backend as part of BuildIt itself, where the user can annotate specific loops or specific statements as like FPGA, and it will do some pattern matching and convert that to some FPGA code. It's generating HLS in this case, so it's still C-ish code that we're generating, but with some special pragmas and some modifications.
And you have some compiler that takes the C code, generates the FPGA code.
Yeah, HLS would do that for you.
So what?
HLS, high level synthesis. Okay, and that's what I call the Quasar of BuildIt, just because I heard expanding. And this is our website, which all has the details. Okay. And then that's my personal website. We'll get back to it later. But I want to take this opportunity to thank a bunch of people. But because there's a short time, I'll do this very quickly. First of all, I want to thank Saman for all his patience and guidance through these years. A lot of what I've learned today, basically all of what I know and research has come from him. Especially since he talked about me before, I'll say this very a specific thing, which is Saman has always taught me to look for problems that are big and trying to solve problems that are not just hard or easy, but to things that really matter and pick problems very carefully. There's a lot more sort of to thank for, but I'm moving for now. Also, I want to thank Professor Mania, who has been a long-term advisor and collaborator for us on many of these projects, and she has taught me a lot about networks and like looking at things that have been done in the area before trying to reinvent the wheel, which has been very valuable. I also want to thank Srini, who's my committee member, but also my academic advisor. He has been very, very helpful in the whole process through ups and downs, has guided me through what to do during my PhD. And finally, I also want to thank Martin, who's my committee, Professor Martin, who's also my committee member. And I've had good conversations with him in the hallways. His perspective on PL has taught me a lot of things. And then I also want to take this time to thank my family, my loving family, my mom, Sangeeta Brahmakshatriya, my dad, Ajay Brahmakshatriya, and my sister, Sai Brahmakshatriya. Their sacrifices, support, and sort of loving nature has brought me where I am today. They unfortunately could not be here today, but they are on Zoom listening to this right now. So thanks, mom and dad and Sai. I also want to thank some of my mentors, Yunming and Changwan, who are present here. Yunming is on call probably, and Changwan is right here, who has taught me a lot about GPUs and writing DSLs. There's a Julian too, and also Mary, who has been so welcoming and thankful for this whole 7 years. Here's the list of all the sort of masters and undergrad students I have worked with. They have been great, and I have learned a lot more from them. The last 3 are external collaborators that I have worked with on some of these projects that I talked about today. So I want to thank them for sort of their help too. And finally, all my friends, many of whom are present in the crowd here, thanks for supporting me through this whole journey and standing behind my back firmly. I would not have done it without you guys. Thank you so much. Sorry?
What is the plane?
Oh, so that is a friend who doesn't like a picture to be put on public, but his name is Ted. So, hi, thanks everyone, and finally, the website and this is.
Bunch of questions from the audience and also people who are on. Can you see if there's any questions get posted there?
Don't see any questions.
Okay. Yeah. Just type in a question or just mic and just speak. Okay. Questions, please.
I will look at what whole the match.
So with your net block thing, you brought up TCP and UDP. One thing I thought of is a lot of people use this thing that has other features called Quick or HTTP3. And this seems like a really cool tool for like, implementing something like that. One cool thing about newer protocols is that in addition to having like very optimized at the packet level, there's also parts of the protocol that are optimized, like there are fewer round trips or different things are done at the same time, like maybe a 0 round trip handshake where you guess some cipher for ELS handshaking. Do you feel like this approach can also be used to optimize protocols? Like
So it does. It does. So all these modules that I talked about that implement specific features, they are built in code, right? So you could have, we already have part of it specialized based on some parameters. You could say like you could say skip the handshake part of it, and it would just have an if condition saying if handshake do this, if don't do this. And it generates code based on your choices. So these 864 choices that I showed, some of these are basically also a result of combination of like choices. So for example here, so routing, so for example reliability, we have, or in order delivery, we have three different flavors of it, which says the first is no in order, it just says don't go in order delivery. The second is drop out of order, where it says if a packet arrives out of order, just drop it. The third one is to keep it in a buffer and then reorganize it and then send it back again. And all these are just implemented as conditions in your modules. Like I showed the graph DSL example before, you could just have first stage variables selecting what features to sort of implement. And that gives you combinations of it. So we actually have zero round trip handshakes and stuff built into it already.
More questions?
Yeah.
Okay, going once. Okay, your question? Okay, going twice. Okay, if you have no questions, I think we are going to go to a closed session, and I think we'll go to switch off the Zoom, and then if yes. Yes.